Hello there. Today I'm talking to Adi Fuchs, who is an expert in AI acceleration technology. We talk about a whole bunch of things in this interview, but it is a little bit of a special thing because it's not about a paper or anything, but it is about a series of blog posts that Adi has authored. I am very much a noob in the AI accelerator field, so I thought it'd be really cool to talk to someone who really know what they're talking about, who are in this industry and can explain everything, from very technical to very noobish for me. So we go over a whole bunch of things like why do we even need accelerators? What are the reasons behind it? Why are GPUs here and why are they good for AI? Up to very, very modern approaches to AI accelerations, TPUs and beyond that. So if you're interested in this, watch the interview. It was very cool. I learned a lot and I hope you do too. Without further ado, have fun. Hello, everyone. Today, I have Adi Fuchs with me right here. He is the author of a series on Medium called AI Accelerators. And I have noticed in the last few years and certainly months that I have no clue about hardware. My conception of hardware is something that goes v, and if I want a neural network, I need like a GPU that goes v, and then there's TPUs, and then there's IPUs, and there's lots of stuff, but I never had any clue what any of it meant. So this article series was really valuable to me, and I thought maybe it's valuable to some of you too. So Adi, thank you very much for being here.
Yeah, thanks for having me, and thanks for the kind introduction.
Can you tell us a little bit about how what your background is in this space? Why did you decide to write a series like this, and why did you think that you had the knowledge to do so?
Well, so I've been back and forth between, I would say, industry and academia. I've been working for several hardware and software companies, Philips. I also worked for Mellanox. I also worked for Apple for some, short period. And I've been back and forth. I did my master's back in Israel, and then I did my PhD at the US at the Princeton University. And I always, my studies have been mainly focused on computer architecture. More recently, my experience has been with computer architectures, processor architectures in general. There's a lot of software going on into it, but from the architectural perspective is how you can design systems that can execute these applications very efficiently, and there's a myriad way of actually doing so. So after my studies, I started working for one of the big companies in the landscape, and I said, actually, when I graduated my PhD, I always had in the back of my mind that AI and machine learning and deep learning, all that has been very, very exciting. I took just like one or two classes, but I didn't really have any extensive experience in it. But I do feel like I was able to see that potential. And I wanted to say, okay, one of the natural things for me after I graduate would be to work for one of those companies that are developing hardware for AI. But the story goes well beyond just hardware. People right now understand that they need to develop smart systems, smart software. It needs to be a full stack view, just going beyond just like you said, the GPU that goes or the TPU or the underlying processor or whatnot. So the landscape seemed to be very exciting. It's rapidly evolving. There are a lot of solutions out there. And I thought that, as a hobby, what I did, it's just started as a hobby, just observing what people are doing, trying to look at the competitive landscape and try to see if there's anything that could be interesting for someone that wants to know more about that world, either be it a research scientist that wants to know a little bit of what's going on under the hood, or people that are hardware engineers that wants to know a little bit more about, the high level motivation for why people are doing AI accelerators. So I was hoping that I will be able to create something like that that will be able to contribute to several types of people, I would say.
Very cool. So my question is a little bit, why, what does it even mean to build hardware for something? Like, obviously, we have computers, and I can do pretty much anything with a computer. What does it mean to say make hardware for AI? You have this term of user to hardware expressiveness. What does that mean?
So I would say I would, as I said, it's more of my term in lack
Hmm.
of a better term. I would say that probably people have several either academic or industry more accurate ways to depict this. Is that the user knows on the high level what they're doing, what they want to do, what type of models they want to explore,
Hmm.
and how they translate it to high level code, like Cafe, PyTorch, TensorFlow, and all that. So the research scientist has the big model that they want to explore. But under the hood, there is what the hardware understand it, what it can execute. So if you look at it, you can see that there is a lot of layers that you need to go to that you need to lower from the high level code all the way to the bits that are basically executing on the electrons that are flowing. And it gets really, really complex because you need to have a full stack view and really know whatever crazy idea that the user is doing and whatever and the last low level detail of everything that your hardware basically can execute. You know,
Hmm.
either degrees of parallelism, how it accesses the memory, be it DRAM, high bandwidth memories, HBMs. There's a lot of things that are going on. What are your precisions? Are you doing FP32? Are you doing FP16, BF16? Are you doing integers? What is your bit width? And there are a lot of details that someone needs to understand in order to build a full-fleshed, fully capable compiler stack that you can basically write whatever you can think of, and it'll out of the box be not only working, because as you said, you can basically compute everything, right? I don't know, Church-Turing thesis. A computer is a computer, but there is a difference between just solving the problem mathematically or accurately and actually doing it in a performant fashion, because you can either solve a single problem and it will take a month to run, or you can solve the same problem and it will be more efficient and it can take, I don't know, like a few hours or even a few minutes.
Hmm.
So that's the idea of user to hardware expressiveness. The user
Yep.
can think of whatever and the hardware can execute whatever, and you need to bridge that semantic gap between them.
And okay, let's say we agree that we need to build hardware for AI. You go through a little bit of the history of that, I guess, starting with what everyone knows, which is kind of Moore's law, that processors or number of transistors increased over time in an exponential fashion. But then you go into some less known laws like Dennard scaling, all of this leading up to saying, we've reached the end of clock frequency. I think this is also known. What's also known is probably that we have replaced essentially speed with number of cores, and we're going into parallelism now. You draw an excellent comparison to GPUs here, GPUs being the current super many core architectures, or not current, but in the history, they had more cores. What makes GPUs so attractive for AI in the first place?
Yes. So I think this goes back a little bit to more of the intro. You're
Mm,
just saying hardware and you're saying computer, but the fact that you can compute things at certain speeds have been key enablers. I go in the introduction, I'm talking about AlexNet, right? You
mm,
see in the AlexNet paper, they say in the abstract, we were able to develop a GPU implementation, an efficient GPU implementation that allowed us to crunch a lot of data and train a lot of data within a reasonable time frame. and get a super fancy model that can run efficiently and within reasonable times. And that basically was a key enabler.
Yep.
What I didn't even mention is that for example, for natural language processing, the same story happened. If you look at the attention is all you need paper, they were able to say in the abstract, we were able to train it on GPU for 3.5 days, which was order of magnitude faster than previous solution. You know, all those LSTMs and RNNs that have this inherent sequential part that we were able to devise a new architecture that is able to run on hardware. And just by being able to harness the power of GPUs, we were able to run, and it basically unlocked our capabilities. So the ability of hardware has been, the role of hardware has been very significant in basically being the key enabler of AI capabilities. And that's why I think this series is very important. Going back to our discussion, you know, trying to talk about frequency, it's good to know about the history, because when you're talking about AI accelerators, is essentially, why do we need accelerators? Why now? So as you can see, as we said at the beginning, there was frequency. We were able to get our circuitry going faster. You can say that, okay, we back at the 90s, you can have like this 486 going at 33 megahertz all the way to like 100 megahertz. Then came the Pentiums, and people will say, yeah, I have like, I don't know, like 300 megahertz, and then you go to like a gigahertz. And then it ultimately going to the Pentium 4 with like 3 or 4 gigahertz. Back at the time, you know, during that time, people understood that because you're not able to do Dennard scaling, you know, that the Dennard scaling, what I mentioned there, is the actual real problem. You know, going beyond Moore's law, the Dennard scaling says that it's not only that you can have smaller transistors, they can also go faster, and you can cram more transistors, and you can have like, if your dimension scales by k, you can have k to the squared number of transistors. Each one will be k faster. And the key enabler there was that you were able to, you know, to lower the voltage by that factor. The thing is, back at the 2000, the voltage stopped scaling at the rate that you were able to increase the frequency. So you can get faster circuitry, but your power density essentially increases. And that's where you can see that the graph that increases. And then people say, okay, we cannot have faster transistors. So that was the first stage in the evolution. Cannot have faster transistors. You can see like the green dot is basically plateauing. And say we cannot, so the implication is that we cannot have a single task going faster, but as Moore's law saying, we can still have more transistors. They just cannot go faster. So instead of having one task going fast, we're going to have multiple tasks going at the same speed. So instead of, you know, increasing the frequency twice, we'll have twice the number of cores. And depending on how we can map the problem, how efficiently we can map the problem, we'll be able to still get 2x by essentially parallelizing. And that was phase 2, which is essentially the multi-core era. So you're able to cram more transistors. They'll be able to getting on the same silicon wafer or the same silicon die. You'll be able to get twice as many cores. And as you can see here, the green line, especially for GPUs as the main beneficent, you're saying, let's develop these, instead of having this design, which is the CPU, which has all sorts of very sophisticated mechanisms, like stuff that there are branch predictors, prefetchers, and all these speculative things that are saying we can execute an instruction, but this will take too long. We can do out of order execution, doing all sorts of tricks to make a single stream of instruction go fast. Instead of it, let's redevise our software a little bit and break the stream of instruction to several independent stream of instructions that are called threads. And we're going to be able to run them, hopefully, in a perfectly parallel fashion on different, what we call cores. And each core will execute its own stream of instructions. So essentially, we'll break up one task into multiple subtasks. And by that, we'll be able to still get the same degree of speed up If we'll be able to get it
Mhm.
to be able to get like 2x tasks, we'll be able to get a speed up of 2x. Obviously, there's a lot of difficulties, but that's the main idea. So we'll be able to, so eventually, if we have enough parallelism, we'll be able to get to, hundreds or even thousands of cores, and we'll be able to get hundreds of thousands of speed up, compared to our regular task. But at I would say the beginning of the around 2010 and 2011, there were two different works that highlighted the same phenomenon, is meaning that, because the NART scaling, again, we're not able to scale the voltage. Just having transistors powered, not even doing computation, it doesn't matter even at what speed, just having them powered on will increase our power density, meaning Moore's law is still working. We can still shrink down the transistors. We can still cram more and more cores into the same silicon square millimeter, in the same silicon area. We'll be able to get more cores, but the power at that time will not remain constant. So the power also increases. So that will be unsustainable. And this has created the phenomenon that these works are talking about, that is called either the utilization wall or dark silicon.
Yeah, what's
That it
that?
means that, you can have, let's say, it doesn't matter if you're going to have a million core with micro transistors. It means that not all cores can be turned on at the same time. Meaning, for the purpose of your computation, you're going to remain under a fixed budget just due to power constraints. So basically what it means that you're not going to be able to get more transistors. And at this
And
point,
so the power constraints are mainly due to us not being able to cool down a thing that consumes more power.
Yeah.
Or what are the constraints there?
So the constraint is that the power density, the watt per millimeter square just starts growing exponentially as you start exponentially cramming more transistors, because the power per transistor stops scaling. It remains constant. So you'll have 1000x transistors, you'll have 1000x the power. And that creates a problem. That will be unsustainable, and that will require cooling that either does not exist or is super expensive to manufacture. So, and that created a problem that essentially says that, okay, we're not going to be able to get more transistors. So if you're not going to be able to get more transistors, then came the notion of building accelerators, meaning that instead of having a single piece of silicon solving a wide range of problems, you're going to be focused on a little bit of a narrow scope of certain applications. And those applications needs to have some properties. So, and that's the idea. If we're not going to get more transistors, we're going to be able to create smart, purpose-built circuitry with purpose-built compute and memory and communication that is basically targeting specific problems. You can see an example like video encoders, Bitcoin miners, and AI. Yep. So you can see there, if you look at more general purpose processors, if you can look at power efficiency or even performance, you can see that the general purpose processor does fairly well for a wide application range, but those accelerators are, for example, for FFT or graphs or matrix multiply, they're really good at a certain task, but they do really poorly on something else. For example, you cannot run your operating system, or you cannot. It wouldn't be recommended for you to run your operating system on an AI accelerator. So
well, wait, just wait. Like the community's gonna figure it out. You just need to scale enough. But I guess I think from this point on, it's sort of common, let's say common knowledge again, that GPUs were purpose built for graphics, but inherently that meant kind of matrix multiply things together. And then on the other hand, deep neural networks, just by happenstance, by being convnets or feed-forward networks, also using a lot of matrix multiplies. And I guess that was just, how the universe works. These things came together, and that was just a really neat fit. And the point, though, is the GPUs weren't made for AI in the first place, even though it seems to be like a really good application for them. What's GPUs are good for AI, but what can be even better, right? Like in which places are GPUs still suboptimal for the AI things that we are doing?
Well, it really depends on your application's demands and the application scopes. For example,
Mhm.
you can see like in the map that you're showing here, you can see that GPUs are really good at flexibility, and they're really good in having matrix multiply. As you can say, linear algebra is something that GPUs do pretty well. And if you can map a lot of these problems, like a lot of confs and recommender models and all that, you can map them into a GPU and do dense linear algebra pretty well. That will
Mhm.
give you a fairly good boost. But if you could devise a certain, if you would go all the way to the efficiency and doing something really, really specialized, you'll be able to say, let's develop an accelerator that just does ResNet, for example. That'll be really, really
Yeah.
contrived to collapse to a certain type of network. Theoretically, everything will be hardwired. Even the weights and everything will be perfectly, perfectly fit for that, but it would
Yeah.
not be able to execute anything else. So if you would
Yeah.
be, yeah, it'll be very, very bad in doing other more general purpose AI. So that comes the question, how can you trade flexibility for efficiency? For example,
Mhm.
one of the things that some of the companies that are not GPU based companies are tackling are these large language models. For example, those GPT-3s and all that. And
Yeah.
GPUs, if you look at the A100s, you can see that GPUs I would say that it was a conscious engineering decision for NVIDIA to go for high bandwidth memories, I'm sorry, that are basically fast memories, but are limited in capacity.
Mhm.
Alternatively, you can go for something else. You can go for a slower DRAM-based memory. So HBMs are fast, but they're limited in capacity, and DRAMs are huge and have like terabytes versus, dozens of gigabytes. And if your model requires terabytes of data, you would need hundreds or even thousands of GPUs just to be able to have to do everything in memory, to have the
Mhm.
same, to map the memory space of your model. And that would be something that, I'm not saying that GPUs can do, but it would require a lot of GPUs turned on and a lot of power and a lot of communication going from different GPU systems to be able to train a single, like hundreds of billions of parameter model. So,
I mean, that's exactly what we see, right?
right.
Okay. So yeah, I guess we can just dive into what kind of hardware that goes beyond GPUs exists. That is to say, in part three, in part three of your series, you go into a little bit of the architectural foundations, and you describe kind of what exists, what instruction sets are, what kind of models exist. For example, reconfigurable processors. You make sort of a good, very extensive background overview, which we're going to skip right now,
Yeah.
just due to time. I just found this very, very funny. I guess that's why you posted it here.
Yeah.
So there is this is a single instruction on that I can use on an Intel processor that computes approximations to the reciprocal square root with less than 2 to the negative 28 relative error of the packed double precision floating point values from these things, and stores the result in that thing with right mask
Yeah.
K1. That is excellent. Like I need that instruction every day.
Yeah. So,
But yeah.
depending on the way that this is basically showing how you can devise when you look at a processor, the traditional model of processor is called a von Neumann model. You're saying
Mhm.
that you have a processor, your processor accesses the memory, your processor fetches an instruction from the memory, it decodes the instruction and says, oh yeah, we should do this and that. So this instruction accesses the memory and loads. Let's fetch the next
Mhm.
instruction and do that. So the instructions are basically built from an ISA, which is the instruction set architecture, which you can think about it as the vocabulary in which the processor says. The processor
Mhm.
supports. Some processors support x86, some processors support ARM, and so which is, I would say, like the x86 is an example of what we call a complex instruction set computing, or CISC, and ARM is the RISC. So there was a trade-off between how much you're going to be able to have a single instruction compact nicely, which will take less memory. So you're going to have a large vocabulary to express more complex computation versus the RISC, the reduced instruction set computing like ARM, that it's going to basically be translated to a lot of micro instructions that will be simpler. So that was an
Mhm.
ongoing discussion, but this gives a background of how basically a processor works. So
Yeah.
there are a lot of concepts that I showed at the part 3 that were basically used as the background for part 4. Historically,
Mhm.
I wrote part 4 as the combination of part 3 and part 4, but a lot of people just advised me that this is just going to be super long, so I needed to break it down. So,
Yeah, so if anyone wants the background, this article is really nice on sort of the foundations of all of this if you want that. And I think people can relate a little bit because in NLP you have this whole tokenization problem of, how big do you make your vocabulary, and if you make it too small, you're going to have to break down stuff into smaller pieces and so on. Just I think it's approximately the same concept right here. You're trading essentially memory for speed.
mhm. And also the thing is that you need a very smart compiler to look at your
Yeah.
code and say, okay, these sequence of, if, for example, if you're writing in C, so these sequence of instructions are going to be translated all to that single instruction. And that way
Mm.
you'll have a smart and very, very complex compiler that will be able to map your sequence of operation into that. Sometimes it works, and sometimes you're just going to have like these ghost instructions that no one's really going to use. So,
So here in part 4, I think it is the longest part, and you dive into the various companies, startups that exist today building AI accelerators or AI hardware in any form. And we have to say that you are associated with one of those
yeah,
companies. We're not going to say which one, though, obviously with the best one. Um,
obviously.
but but I felt reading the article that there was no I didn't feel any favoritism, so I was pretty happy to see that. Now we have a lot of them even discussed in your articles. Do you maybe have some that you wanna highlight in particular to just maybe show the diversity of the field and where it's going?
Yes. So while there are a lot of solutions out there, I would say most of them stem from a handful of a few architectural ideas that were highlighted in
Mm,
part 3. So I would say that originally there's the GPU with the CUDA
yeah.
that has dense linear algebra that is basically
Hmm.
has this this execution model, single instruction, multiple thread. It's the idea of the classical von Neumann model. You have instructions, they're translated to processor level ISA, that the instruction set architecture that NVIDIA and GPUs understand. And it's being
Hmm.
parallelized, and it has all these systolic like execution. And a systolic array is an idea that dates back to the 1970s, where you're going to have a single piece of hardware that is really good in doing matrix multiply, because the data when you're doing matrix multiply, the data from the A and the B matrix is basically flowing like that. And if you have a very smart circuitry like that, which is in a sense a smart accelerator-like engine just for matrix multiply, it'll be able to carry out matrix multiply really efficiently. So the GPUs have that, and you can say that there are some other companies that I would say that are in the camp of VLI, a combination of what we call a VLIW, a very large instruction word, where you're going to have a heterogeneous array of compute machines, like a memory compute machine, a vector compute machine, a matrix multiply, and maybe some sort of a linear compute machine for your ReLUs or tangents operators and whatnot. And you have a static compiler that basically creates this huge instruction that says, okay, this data goes to the vector unit, this data goes to the matrix multiply, and this data goes to the vector unit, and you're able to, and the timing of all these units, and you'll be able to have a smart compiler that statically creates this single word that is going to be fed to all of them. So you can have at compile time, a smart compiler that will be able to efficiently schedule these different data or operands to these machines, and they will be able to get really efficient execution. So I would say the Systolic / VLIW camp, I would say things that are, arguably the most famous example is the Google's TPU that was presented at, I would say, mid 2017 at a conference called ISCA, the International Symposium of Computer Architecture, which is the biggest computer architecture conference. So they showed a model that is basically, the TPU is based on a big systolic array execution with a linear unit and this smart memory, and everything is being fed, and they have a smart compiler that translates AI code for that is able to execute DNNs, these deep neural nets. And that was the first time, arguably the most famous non-GPU AI accelerator that was presented. So you have the Google TPU. You also have a startup that is called Grok. Some of its founding members were part of the Google TPU team. There were architects at Google that took parts of that took some of the ideas of Google's TPU and created a more commercialized accelerator for deep neural nets. And also there is Habana. So I would say Google, Grok, and Habana are, I would say, the camp VLIW plus systolic array accelerators. So
so I understand this correctly. They essentially have a chip or a board, and that has many different, let's say, sub chips on it. One is really good at matrix multiplying, one is really good at doing ReLU, one is really good at whatever softmax. So kind of all these operations that we need in AI, they have like specially sub chips for, and then they have a very smart, essentially, router that says, okay, you go here, you go here, you go here. So, I could compute, let's say, I could compute the last layer's ReLU at the same time, or the last batch's ReLU at the same time that I compute this layer's forward through a linear layer. Is that,
this is essentially like you're
correct?
Basically pipelining it. So if you have one thing that needs the ReLU, and then one thing that needs the matrix multiply for the conv operation, then it needs the ReLU, and then you can feed the next sample or whatnot that uses the matrix multiply while the other one also already doing ReLU. So you can do like sort of a pipeline execution, and by that you're basically filling up your compute machines, right? And by that you're getting better utilization because you're using all of your hardware at a single point, and everybody's happy, and your architecture is perfectly balanced because your compiler is smart enough to understand the program.
Yeah. So essentially, we're saying we want the purpose-built hardware, like the unit that just does ReLU, because that's way better than having a CPU do ReLU. But in order to have the flexibility, we have a bunch of them on a chip, and then we have a router and the compiler that knows how to use that router and the pipelining.
Yes.
Okay, excellent. But that it seems really it seems like, just from me now, it seems a little bit still in the spirit of like a GPU, of what you said, that you essentially have this von Neumann model, except here there's sort of pipelining added, there is distribution to different subunits added, right? But it's still these kind of instructions that are in sequence, and the compiler needs to understand how to translate a program into that. And as I understand, the other companies here, they're trying to go sort of bit more out of that paradigm. Is that
Yes.
correct?
So I would say the other big directions that companies are doing is the data flow directions. So some companies are combining two elements. One is called reconfigurability, and the other one is called data flow. So their reconfigurable data flow, I think that Tenstorrent are doing it. I think that Samba Nova is doing it. Originally, there was a company called Wave Computing that did it. There was another company called Simple Machines that are doing it. So the idea of reconfigurable data flow is that, first of all, if you look at a PyTorch or TensorFlow or Keras or a Caffe program, and an AI, a deep learning application, you can see that there are different layers and they're communicating with each other. So you have a predetermined set of operands, and you know how the data is basically being communicated between different parts of your graph. So in the underlying computation is basically constructing of a computation graph. What does that mean? Like you can see over there, you have your layer, and from that you have another layer that does ReLU, and then you feed it to another conv layer or weights and do that. So you have basically something that is not instruction level, but basically more of the way that your data, you can see that your data is basically flowing between different layers. So the idea is that instead of having that program, that data flow communication graph go, you flatten it to the classic von Neumann model, then you try to reparallelize it. You can start off from this data flow model, from this data flow graph, and you can basically statically map it via another. Again, you need a smart compiler to do that as well. You need to map it to your existing, to a specialized hardware that is capable of executing data flow, meaning you can have a compute element that does multiply in here, and you can have another one that does add in here, and you can basically break down your dense linear algebra to compute unit, and you can feed them to other compute unit instead of breaking down your computation to micro unit, like saying, oh, here's an add, then, oh, you need to multiply and all that. So it would be more natural to look at the looking at the computation graph as a data flow graph and map it to the hardware, and you can start it instead of going back and forth, flattening it to the von Neumann and then reparallelizing it to the von Neumann. So these companies' bets are that this model is more natural, it's more hardware friendly, and ultimately you can get a better gain because you're able to have a better, more complex understanding of the graph. You can look at different elements in your graph. You can have a smart compiler that fully understands your hardware. It knows the number of compute elements and what each compute element in your processor, in your accelerator is doing. And from that, it will create a mapping that will essentially be very static, and your data is just going to flow instead of you needing to manually orchestrate it and breaking it down to instructions. So, one of the main selling points of the existing landscape like GPUs is that GPUs are they have a very mature software stack, and they're very flexible. You can program everything from that von Neumann model. If you can create a flexible enough architecture, you'll be able to basically handle new models, because the main challenge for you to build an accelerator company is that it takes 2 or 3 years to tape out a chip. Meaning you need to think about your idea, you need to think about your architecture, all of what you can execute, and you need to be generic enough, because within 2 or 3 years, it's possible that your application has completely shifted away. And if you look at those, the mapping of specialized accelerators, if you're here, but your application space is moved here, you're not going to be able to execute it efficiently. So you need to be very open-minded, and you need to be very mindful about being flexible enough to support this. One of the main challenges for that is the ability to create a smart enough software stack that will be able to execute it. So it's not a trivial task. So you can take the wave computing case as an example. Wave computing was a company that was really revolutionary. They were able to present a commercialized accelerator that does reconfigurable data flow at the beginning of 2017. So they had, a fancy hardware with 15,000 cores running at 6.7 gigahertz and a lot of engineering complexity that is able to have both slow memory and fast memory and all that. But from what I understood, that the CEO interviewed and say, okay, we were not able to succeed in it because it was so complex that, going from the basic cases where we were able to showcase a few kernels, trying to generalize that to more complex and real world application, we found that our, hardware software stack had to solve intractable problems, and that would become unreasonable. So I would say that their problem was that they were way, way ahead of the curve. People were just exploring these problems, and they were not able to estimate those difficulties. They were pioneers, but ultimately, it didn't pan out so great for them, because eventually they filed for bankruptcy.
There's also this concept of in-memory compute or near-memory compute. What is that about?
So there are several notions of how close the compute and your memory should be. So one form of near-memory compute is saying that you have your memory model, and from that you're loading it to what we call a software control scratchpad memory. So you have small, fast memories. You can think of it like as a processor cache, but they're software control. Traditionally a processor cache, like in the von Neumann model, is basically has a heuristic of, saving the most recent accesses just because this is like the hot data.
Yeah.
And a software-defined scratchpad memory is something that is more compiler controlled, that how you're going to be able to access. One of the things that one of the guiding principles of devising an accelerator is that you're basically able to anticipate how your memory and data accesses are going to be like. You're going to have a handful of basic computational structures that you're going to iterate over a lot of data, and it's going to be really recurring. That's one of the things that enable you to develop an accelerator in the first place. So a scratchpad memory is a fairly small and fast memory. It can be kilobytes to like a megabyte of data that is really close, and it sits within the same piece of not even the piece of silicon, but within the same core within that piece of silicon. And you'll be able to communicate that data fast. It will take like 1 or 2 clock cycles. Another approach would be a processor and memory approach. That's when the processing element sits really close to the actual memory model. If you're going to manufacture something like a DRAM or something that is called memristors, which are memory-based resistors, you're going to be able to manufacture a memory module that is going to have logic elements inside of it. And you can see of those examples like Mythic or one of those companies that are developing what we call the processor in memory, is the idea that you can look at deep learning computation, and you can look at the dot product, and from that you can do analog computation, but that will be fairly complex. But the idea is that you don't really need to fetch back and forth data from the memory, because it's all within like this special circuitry that sits within your memory module. And you're saving a lot of that energy going back and forth from the memory chip and into a different chip, which is the compute memory, the compute processing element.
So it's essentially like having a lot of, like, given that we already have a lot of cores, that we also have like lots and lots of registers at those cores, but the registers aren't just for, temporary data, but they are actually the memory.
Yeah.
Okay.
So it's, in a sense, you can think about it as, the difficulty is that you needed to really change the memory that you're manufacturing. That's something that not a lot of companies are doing, but it's a promising direction, because, if you have something that is less dependent on your transistors, so it's less prone to the failures of Moore's law. So the end of Moore's law might not be the bottleneck for some of these modules, but there are other things, like you can see that there's like an analog to digital converter, which could be power hungry, and that creates a slew of analog compute problems. So
there are also a bit more, let's say, call them esoteric things that all of these were already esoteric to me, but there are more esoteric things, like there's like optical computing and neuromorphic computing and things like this. What are, do you have any favorites there, or anything that you think is promising and not buzzwordy?
I think that Light Matter is a company that was founded by a few MIT graduates, and they have this idea that that's representing analog computation via light could be more efficient than using it but then expressing it through the digital domain. It's an interesting problem. I'm not really versed on the different types of difficulties there, but it's sort of like thinking about an analog neuromorphic model where the brain acts basically like on analog pulses. So this is a little bit more trying to mimic the way that the brain works than you would go the traditional artificial neural networks, where you're going to have a BF16 represent your weights, and you can say that this is closer to reality, and it's also more energy efficient. But you can say that these are more advanced technologies, so I would say that they probably have their own set of challenges. And you never know which one of these technologies will prevail and be the winner.
And what is neuromorphic computing?
I think that the neuromorphic computing, as the way that we know it, is the form of analog computing. You're going to have data over here. You're going to have like the weights that are sitting in your memory, and your activation is going to be coming from that memory, as inputs to that memory. You're going to be able to do an analog addition, and instead of doing that dot product between the weights, you're going to have a single dot product doing vectorized compute in an analog fashion, and you're going to be using analog circuitry to compute the results. So it's more similar in theory to the spiking neural network model, where you're going to have like your brain act on electric pulses. So that's what these solutions are trying to mimic.
Yeah. Okay.
Conceptually.
Um,
And
sorry.
that eventually, if you look at hardware from the grand scheme of things, you have those accelerators. These accelerators are good at doing AI, but if you really want to get into the definitions, you can look at the Ian Goodfellow's deep learning book. It's not really AI. There's a Venn diagram where AI, and inside of it there is machine learning, and then there's representation learning, and then there's deep learning. And from within that deep learning, you can say that these accelerators are good at a subset of deep learning and a subset of ML that is good at doing matrix multiplication. They're really good at doing things like conv and transformers. But is that a general solution to AI? No one really knows. You can say that the interesting thing is that because the hardware was a key enabler, it's also sort of used as a limiter to what you can achieve.
Yeah.
People are saying, is attention all you need? Is conv all you need? Could be, but one thing is for sure is that it consists of most of what your hardware can do. Your hardware is really good at transformers and attention and convs, but if there is that how intelligence really work? Maybe there's a huge slew of applications that can mimic more human intelligence that are not that cannot be efficiently ran on hardware accelerators the way that they're built today. And we're not going to be able to explore it just because we don't have the hardware for it and we don't have a way to run it efficiently.
Yeah.
So it's an interesting problem.
I mean, there is this concept. People say this, right? This is a sentiment that's echoed throughout the community that, for example, graph neural networks, we don't have good hardware for graph neural networks, and therefore probably we're not going to explore them as much, which also means that hardware manufacturers, since we can't demonstrate that graph neural networks are really good, won't build graph neural network chips. Do you see this? Do you see it generally going, let's say, more and more converging on some applications? Or do you think, okay, we'll discard some of the applications, but also the ones we have will sort of morph and develop into different variants and so on? Like, how do you see the hardware, essentially the expensiveness of manufacturing hardware's effect on the diversity of the ideas in the field? Do you think there is hope to increase diversity even with the cost of hardware?
It's an interesting question. I would say, obviously, money makes the world go round. If there's money within these applications, you're going to be able to build the hardware for it.
Mm-hmm.
The thing is, like we said earlier, hardware has been a key enabler for what you can achieve. And basically, if you cannot run your application on hardware, it will be hard to create that ecosystem for that application to be able to justify building specialized hardware for it. So it's a bit of a chicken and an egg problem.
Yeah.
If I were to develop an accelerator for a non-Euclidean set of problems, I would first need to look for the applications for it. I will need to be looking for that justification for it, simply because, if I'm a startup company, I'm going to have to need funding for it, right?
Mm-hmm.
But if you if you don't have people that are exploring it just because there's no hardware for it, you won't be able to find that justification. So it's a bit of a chicken and an egg problem. Mm-hmm. So as I said, maybe attention is all you need. Maybe conv is all you need. For surely it's most of what we have right now. And it would be interesting to see. I would say that, as I said in the final thoughts, I would think that in the next 2 or 3 years or so, the things are going to become clearer and architectures are going to be able to stabilize just because we understand the problem better.
Yeah.
It will take us like 4 or 5 years to really converge to a set of common practices in the way that we're developing hardware, the way we're developing software libraries, and the way that we're developing compilers. We're going to be able to have like this, I would say, like 3 or 4 stable software stacks that are really good at the conv and transformer games. Mm-hmm. Will there be other models to create other stacks? Sure. But if I were to start a startup today, it will be really hard for me to go for, the conv and the transformers, just because, this is saturated field and people are doing it fairly well, and you're basically almost maximizing what you can do in your hardware.
Yeah. You have the last saying here in your final thoughts is everything old is new again. Do you wanna explain what that's about?
Yes. So there are a lot of, it seems like there's a bit of, you can say that on one hand, these models have been the most popular models, those key enablers, those AlexNet and those ResNets, those attentions and BERTs and the GPT-3s, they all originated in academic papers, right? But in the hardware field, there's a little bit more of a disconnect. I would say that there are a lot of papers, there are dozens of papers presenting new ideas every year in the top conferences. There are the ISCA, HPCA, ASPLOS, and Micro. But eventually you can see that all these accelerators were basically using ideas originated like 30, 40 years ago. Processing in memories was, I would say, in the 1980s. VLIW, again, the 1980s. Systolic arrays, the 1970s. Dataflow programming is the 1970s. Processing in memory, also like 1970s. So it's a bit of conservatism because, as you can say, that a company building hardware knows, at least in the older days where it was hard to get funding for it, you would need to really, really justify and really go for these well hashed out ideas before you would go for those wild card ideas. And once you have that, you might be able to explore more revolutionary ideas. Unfortunately, I think that at this point, a lot of your architectural foundations are already established, so you won't be able to explore this crazy accelerators or those things that are, really, really out there. You'll be able to somewhat integrate it into your existing architecture, but it would be very daring to go and break your entire architecture completely. And especially in a very competitive landscape, you might not be able to go for that risk.
You would be surprised, but there are many people in the AI community that say that all the AI ideas have been had in the 80s and 90s as well, and there's essentially nothing new under the sun. But it's a debated position, let's say.
It's a debated position. Well, I would say that for one thing, for sure, the going back to the attention is all you need and conv is all you need, and essentially is what you got. A lot of these, the basic computational structures are already there. People are building on the baseline of these architectures simply because, for me as a hardware architect, from my perspective, this is what the hardware can do. It even goes back to this academic notion of accelerators. There's a work called Stream Dataflow Acceleration that was presented in ISCA of 2017 that they're saying, okay, the acceleratable domains need to, they need to fulfill certain properties. They need to have like a fairly confined control flow. They need to be like fairly repetitive. You need to know how the data reuse. You need to know a lot of how your computation patterns behave. So, if you're not going to be able to build an accelerator that completely breaks out from this common wisdom and breaks out this template, you might not be able to have an AI model that behaves that way. Is it true or not? could be or could be not. Maybe we will find out that our existing patterns are fulfilling enough. I would say that there are a lot of problems even within the existing architectures that we were able to fully explore.
Cool. Is there anything else you'd like to want to give people on the way? I guess there's not an easy way to necessarily get into, hardware yourself at home or something. But if people want to dive, they can certainly go to your articles, which I think are great. I will obviously link them in the video description. Is there any message you want to get out there regarding this?
I would say, I cannot really say anything about looking at the blog. Try to look at high-level overviews of how hardware and software behaves. It's really tightly coupled today. It's a really exciting time to be either in AI or in hardware because it's a really great opportunity from many aspects historically that you can explore AI hardware either as a research scientist, as a data scientist, or even a computer scientist. It's really good to see how all these pieces pan out. Start looking at the high-level overviews and then just deep dive into any of them. Open a computer architecture book. The old ideas are already there. Try to look at the high-level white papers from the big companies. The Googles and the NVIDIAs. And some of the accelerator companies. Try to understand how your software behaves, and you might find out that it's really great that you can execute your models much faster than you have anticipated, because if it's going to take for you 3 days to train your model versus if it's going to take you 3 hours to train your model, that's going to be it's going to be a key enabler to a lot of your capabilities.
Yeah.
So just try to do all those tweaks, try to understand the common practices, try to follow programming books and rules and best practices, and you might find out that you're going to be able to be a kick-ass data scientist.
Excellent. Well, Adi, it was a great pleasure having you here. I learned a lot. Like, really, I had no clue before this. So thank you very much for these articles, and thanks for being here.
Thanks a lot for having me.